Now, we are going to look at the ensembles, and we will say especially in case of the dynamic properties as well as structural properties, and now we look at elastic properties. We really have to understand the ensembles, because these are different thermodynamic situations, and so you need different kind of ensembles for dealing with those situations. So, if you look at, if you are interested in, let us say, phase transition in terms of only energy, then microcanonical ensemble is very good. Essentially, you sample the potential energy surface. Potential energy changes as you change the state space or state variables, and what I mean by state variables once more is thermodynamic variables, temperature, pressure and volume, which connects with the density. So, now if you look at TVN ensemble, where you have canonical, and I said that canonical ensemble is important because most of the Metropolis Monte Carlo simulation revolves around what we call is canonical ensemble. So, in that case we look at TVN ensemble, and then you have constant pressure, which was the Parnello-Rahman formulation, where we look at the vector of three sides of a particular simulation cell, which is allowed to move. So, there is no constant volume anymore, but it becomes TPN ensemble, where temperature, pressure are isothermal, isobaric, and number of atoms is constant, and finally, the grand canonical. So, we looked at one of the very important ideas in canonical ensemble, and that has a relevance primarily because we are looking at the phase transitions in terms of the temperature changes. So, if you look at temperature changes, you have to have a particular what we call is a thermostat, and we looked at thermostats in terms of a temperature reservoir connected with the system with what we call is Lagrangian dynamics. So, if you look at in this slide, this is the Nose-Hoover formulation, where if you look at the momentum differential with respect to time is connected with the force equation, which comes from the potential energy. And then there is another term which is called resistive term, which is what is the friction force connected with the particles, and by increasing friction you reduce the velocity, by reducing friction you increase the velocity of particles, and that is how you can make sure that you have a constant temperature, and that is where TVN ensemble, and you can look at the details about dynamics of frictional coefficient to get canonical ensemble. And we looked at there is that thermostats are needed in non-equilibrium situations, where there might be flux of energy in and out of the system, and that is where you need to make sure the temperature remains constant as you change the thermodynamic situation. It is also important for time reversal to make it deterministic, and if you look at the distribution of the velocity, then goes into canonical distribution, which is connected with the Boltzmann distribution function, which is very important factor that we will learn in also the stochastic methods of simulation. And then of course, the thermostats do create some artificiality in the system, and you can look at some of these effects looking at some of the papers by Hoover as well as Nose, which are given here. Now, we look at the isobaric ensemble, where we know that the volume of the simulation cell now can change in terms of the pressure, and that is where you have to start with the virial of the pressure, as shown in your slide here. You have the virial pressure defined in terms of the volume of the cell, as well as we are looking at the kinetic energy and the change in the configurational energy Rij with respect to their positions. So, if you look at the system can switch between crystal structure, and this method is very useful to study the transition between different crystal structures. So, if you look at with this flexible cell formulation, we are now able to look at automatically finding different kinds of crystal structure with different pressure situations, and that is what I have been referring to as Martensitic transitions. Primarily, you can go from BCC, body centered cubic, to face centered cubic with a transition which is induced by the pressure. So, in this case, pressure related phenomena, whether it is pressure related phase transition or pressure related melting of the system, all of that or different phases of ice under different kinds of pressure, they are all simulated using canonical ensemble, an isobaric and isothermal ensemble, which is what we are looking here. So, if you look at this situation, then we said it allows us to automatically look at the crystal structure. It is a nice feature because the boundaries are flexible, and because of that we can at certain temperature pressure situations, especially in this case pressure, if we keep the temperature constant, isothermal situation, and keep changing pressure on a cube, whether it is compressive pressure or it is a extension or we are stretching it out, those two situations we can look at and see how, based on the bonding between the atoms, what is the elastic constant. And I think that is where we connected with the elasticity and the whole literature about structural materials. And if you want to design material with different structural properties, we now can look at different kinds of phase transition as well as the elastic constants. As you know, elastic constants are very important because material can be isotropic, where elastic constant is same all throughout this material. If you look at a, let us say, metal, if you stretch it from any direction, it will have the same elastic constant. But in some cases, if you have composite material, then you can create anisotropic behavior. So, some material may not have even same kind of elastic constant in x direction, y direction, z direction. Now, you have 9 different elastic constants, and you can look at all those phenomena as we move forward. And that is a situation for isobaric NPT ensemble. But if you look at, in this case, we are essentially looking at the molecules moving up and down. It does not guarantee us to get to the local minimum. So, what it does is that it will provide you the dynamics without regard to the energy fluctuation in the energy surface, and it may lead to some of the situation that are non-physical dynamic situations, and that is where we are looking at the locality of the interactions and some of the non-physical effects coming in. But if you allow system to equilibrate long enough and then provide certain state variables of temperature and pressure, you can see some of these very, very important effects that we want to understand now in the different ensembles. Now, this gives you idea in the when we are solving the equation of motion, but equation of motion essentially is providing us location of the particles at certain time t. So, we start with a location which is initial position of the particles in the crystal structure, then we give them velocity, and we find through the solution of the time trajectory using some of the finite difference integration methods, we integrate the second order ODE and get the trajectory of the atoms, and that is how we will snapshot at every 5 time step or etc. But what if we take all these particles, put them in a crystal structure and randomly move them with a delta x, and then we calculate the energy of the particle. Then we take another such sample and we create 1 million of such configuration, and then look at what happens to the particle as they move around with a random changes in their position. What will happen if we put some kind of criteria in terms of what we call importance sampling, and we sample this statistically, then we are able to understand statistically what is the most stable configuration with the minimum energy. So, what we are essentially looking at, put the particle randomly, do not solve any equation of motion, just calculate the forces based on this new random positions and reduce energy to the point that is the minimum energy. And now, you look at that situation and say this is the most stable configuration. So, by taking snapshots, we are able to come to the same conclusion which we could have gotten by a long molecular dynamics simulation. Now, the problem with this scenario is that I lost some of the dynamic information in terms of how atoms move from one place to another, because I am randomly choosing their location, I am losing some of the dynamical information. However, I am getting the if I am interested only in the equilibrium properties, the minimum energy properties will be equivalent to in the same model as ergodic theorem, that it will be similar to what we did in molecular dynamics. So, Monte Carlo simulation, which essentially does similar randomization of atomic position, allows us to calculate without solution of equation of motion the same thermodynamic properties that we were doing by trajectory calculation. So, now we turn our attention to Monte Carlo simulations. Thank you.